Hi, in this video we will learn about a mathematical constant called Euler's number, E, and we see that when you choose this E as the base of the exponential number, exponential function, we call that exponential function the natural exponential function. Okay, let us start with what is this constant. So, first of all, it is called Napier's constant, Napier constant, or Euler's number. It is an irrational number. We have a name for that. You remember there are other mathematical constants like pi. You choose a name, a notation for that. It was pi. It is pi, Greek letter pi. Here we denote it by E, and well, you may say why. That's why. Is a rational number. We denote it by E, and well, it is approximately is approximately has the value. Well, 2.7181. You can continue this thing. There are other digits. No one can write all the decimals for you because it's an irrational number. And its decimal never stops. There's no good pattern to see those ones. But for us, what you need to remember is that whenever you need it, this is enough. 2.71. Well, remember, for example, for pi, we have the same situation. Yes, we just keep two first decimal of this in mind for us while doing the computations. Okay. Something that you may ask, well, where this number comes from. There are very good stories about this thing, but one of the very important historical ways that one gets into this is that, well, you just evaluate this expression for different integer numbers. For example, 1 plus 1 over 1 to the power 1, or then do for 2, and then to do for 3. It's a good practice. Go ahead and, to the power 3. And try to evaluate this 1 plus 1 over n to the power n for different values of n, and you will see that this number getting closer and closer to a number. It's called, that's the E number, the Euler's number. Okay. Why is this important? Well, this came out very naturally in mathematical modeling, and when we choose this to be the base of exponential functions, so definition, the exponential function with base E, so in other words, f of x is equal to e to the power x, is called the natural exponential function. The natural, it has a reason why we call what, but you just keep in mind that it is the natural one. And well, the graph of that, because you already know what are the graph of exponential functions graph, since the base e is bigger than 1, so its graph is going to be of this form. Okay, let me change this one because I need a better line down there. It is increasing, passes through 1 and then goes down like that. And well, you have again x equal to 0. This is the horizontal asymptote. We will learn about the horizontal asymptote more later, but this is the graph of that function. Let's just as an example try to sketch the graph of f of x equals to 2 e to the power x plus 1 and then plus 3. Let's try this one. Okay, so here we need transformations, remember? So if I start with e to the power x, then I replace x by x plus 1. I will get to, let me write this as f of f0x. Then f1 of x will be f of f0 at x plus 1, which will be e to the power x plus 1. This is definition. Then I need to multiply f of 1 by 2. So then we do f2x, which will give us 2 e to the power x plus 1. And then the last step is that f2 plus 3, which will give us our function f of x, which is 2 e to the power x plus 1 plus 3. What are the meanings of each one? We will go one by one and we will see what do they mean. Okay, so here let me draw this one. Start with this, and then we have this guy here. The first thing is that we are replacing x by x plus 1. What does this mean? This means that we are translating the graph of function 1 unit horizontally to the left. So this is a horizontal shift 1 unit to the left. So if we start with this point 1, 0 here, then you see that I need to do the shift. Actually, I have it here. Okay. So I want to now do the shift. Shift to the left 1 unit. So if this is there, so this will come almost here. And if I want to keep track of that point, this will be now negative 1, 1. Why did it turn to black? I don't know. Okay, this is the first step. The second step is that we are doing 2f1. It means that we have, first of all, the vertical stretch by factor of 2. So let me copy this. Copy and paste. I will need a bit more space here. Okay, and this is what I choose. everything multiplied by 2. So it will go up like almost that. Yeah. Yeah, makes sense. And as you can see, the point negative 1, 1 now, oops, it's going to be at negative 1 and 2 because we stretched that by factor of 2, yes? And the next thing is shifted 3 units up. So this is vertical shift 3 units upward. And well, let me scan. Oops. Yeah. Copy and then paste. Oh, probably need more of this thing here. Okay. Okay. And now I'm shifting this guy 3 units up. This is 1 unit, 2 units, and 3 units. Almost there. Yep. And as you can see, this time our point here will be negative 1 and 5 because we are shifting everything up. While doing all these operations, it's better to keep track of this horizontal asymptote here. When you do shift to left, it doesn't change. When you stretch, it doesn't change. And when you do and when you do the shifting up, it will shift 3 units up. It's better to continue this thing like that. So that is the graph of this function. The natural exponential function is very important. You will see right now, right after this section, that well, the first thing to know is the derivative of this guy, and between all the exponential functions, the derivative of the natural exponential function is the easiest and the best one.